Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour.
Welcome to another episode of On Air Actually Rocket Science. Today, we embark on an exciting expedition to a place where only 12 humans have ever set foot on. It has been over 50 years since the last Apollo lunar module touched its dusty surface. NASA's Artemis program is reviving crewed lunar exploration, and it's not just the US planning human and robotic missions to Earth's only natural satellite. Nations around the world are racing to get access to Moon and its resources. I'm Benedict, and sitting right next to me is none other than Mikkel, my crew member for today. We're excited about today's guest, holding the Professorship of Lunar and Planetary Exploration at TUM. His research is focusing on the exploration and extraction of space resources on the Moon and other celestial bodies. You will guide us on this voyage, and we're happy to welcome you, Professor Philipp Reiss. Thank you so much for being here today.
Yeah, thank you for having me. Hello.
As always, we will start with a quick round of this or that.
So the first one would be Apollo or Artemis?
Artemis.
The second one, rover missions or crewed missions?
Rover.
Interstellar or The Martian?
Interstellar, I would say.
Interesting. Earth day length or Moon day length?
Well, definitely Earth length.
And the last one is chemistry or physics?
Physics.
That took a second to think.
Yeah, actually, I mean, those are quite interesting questions already, and we could talk about these just for the entirety of the podcast, I guess.
Yeah, but I think we need to go on because we have a tight schedule for today because there's so much interesting stuff to talk about. Let's take a glimpse on your career path before up to this point. So to summarize it, you began with mechanical engineering with aerospace focus in Bremen, followed by an aerospace master's degree in Munich. And then you went on one further step and completed your doctoral thesis on in-situ thermal extraction of volatiles from lunar regolith in 2019, also at TUM. So talking about your motivation, what initially sparked your interest in lunar and planetary exploration?
That was starting with studying mechanical engineering. I wanted to become an engineer. I think what first attracted me was the aeronautical world, so building airplanes, flying airplanes. During my bachelor program, I think the focus switched quite quickly to space, to the final frontier, because my view of that was always in your career later on, you need to be motivated. You need to be fascinated by what you're doing. And space exploration is the only thing I can think about that would really keep me motivated throughout my career. So that was what I guess drove me towards space. And I focused in lunar research during part of my studies already with internships in companies, Airbus, for instance, where I was involved in lunar lander development at the time. I decided at some point to pursue a PhD in that topic. I was lucky enough that the time was right. So currently we are in this, as you already mentioned, in this second, some call it space race or the race to the moon. It's quite exciting times. There's also more opportunities to do PhD, postdoc, to work in that field actually than there used to be 10, 20 years ago. And so the natural path brought me to lunar exploration and the place where I'm right now.
Yeah, that's also the reason for all of us students choosing to study here. After completion of your thesis at TUM, you worked as a research fellow for the European Space Agency. Could you explain us what was your role there and what did you work on?
Right. So a research fellow at ESA is a postdoc position. I was part of the Lunar lander team, as they call it. So this is a very small team within ESA, and they are working on lunar missions or instrument developments, contribution to lunar missions, so actual flight missions, not only concept studies, but the things that actually will fly. And so my role there was to support this team from the scientific perspective, because I was doing research on lunar volatiles, on lunar water, prospecting, instrumentation, and this is exactly what this team built in ESA, or is still building. And so my role was more the role of a scientist to advise the team, to also work on the interface between the science and the engineering of the instrument development, but also to supervise my own research activities with consortia across Europe. That was a quite exciting time. So I was at ESTEC, ESA ESTEC in the Netherlands. This is the biggest site of ESA across Europe, and this is actually the place where everybody goes that has ever to do with missions, just to some extent. So because it's a huge site, there's lots of experts there, there's testing facilities there, so it's a really nice place to and environment to work in.
Yeah, so if I get it correctly, there's much of input to get there. Is there some particularly memorable experience from there? Well,
so the thing that strikes me still today when I have to deal with ESA folks there, that the level of expertise they have and the level of professionality that they have there. So and the motivation that you can feel there in the ESA family, as they call it. So it's all about space. And in the directorate where I was in human and robotic exploration, it's all about exploration. So you really feel that spirit. And of course, the fact that at one point we had, for instance, JUICE, so the Jupiter mission that is currently in transit and on the way to Jupiter, was tested during the time when I was there, and my office was just opposite the large thermal vacuum chambers where the mission was in. So the spacecraft was being tested there, and it was just like 50, 100 meters or so from my office. So that was quite impressive to be aware of the fact that such a spacecraft is now right beside my office and will fly to Jupiter in the next year.
Yeah, that really
things like that happen like every day.
That really sounds amazing. Then your next step was going back to TUM and follow on with your academic career. What motivated you to return to TUM after your time at ESA?
So there's not so many opportunities in academia to work in space exploration, right? So this is a very special opportunity, or has been a very special opportunity. And I always wanted to go, or to stay in academia, to do research, also to do teaching, because I very much enjoy, the whole educational aspect. And the research aspect, and so that was one opportunity, and probably the only opportunity for many years. So and I knew TUM from before. I like it very much, living here and working here in the Munich area. I like the mountains. I like the Munich as a city and as an environment. So yeah, that was the perfect fit. Yeah,
definitely sounds like a plan.
So you already talked about that there's lots of new stuff going on. Could you maybe provide us with a quick overview over the current state of lunar and planetary exploration?
Yeah, sure. I mean, that's it's actually not very easy because there's so much going on right now. So in our lectures, for instance, we have at the beginning of each lecture, I give this brief overview of what has happened in the past week. We call it This Week in Space Exploration. And there's always something to tell. This shows you that there's a lot going on right now. So initially in 2023, so this year, it was planned that, 3 or 4 missions to the moon will launch, commercial ones, but also institutional ones. There has been some delays, so some slipped to the next year. But just recently, last Friday, we saw the launch of the Indian mission Chandrayaan-3. So we hope this will be a success. We already saw one failure earlier today by the commercial iSpace lander. We have 2 or 3 more commercial missions coming up. They probably won't take place this year, but beginning of next year. So there's a lot happening. Now to figure out what is happening there in terms of overall structure, I think we have to reflect a bit what is actually happening in terms of programs and how the whole situation changes with respect to commercial missions. So of course Artemis is something everybody knows, right? So Artemis is a program. It's part of a larger architecture, the Moon to Mars architecture, and it's driven by the US. There's also this commercial approach driven by the US called the Commercial Lunar Payload Services, or CLPS for short. This is a program where NASA buys in transport capabilities from companies to deliver their payloads to the moon. And as part of that, there's a few launches coming up. This is a new approach, which still has to be tested and still has to work properly. Ultimately, it will speed up things, it will save cost. It'll be much easier to transport something to the lunar surface for us as scientists as well, but also humans, of course. So CLPS is sort of a part of the overall architecture from the US-driven perspective. Europe tries to play a role in that, providing critical elements to the overall program, like elements for the Lunar Gateway, the station around the moon, potentially also a cargo lander called Argonaut, but also scientific instruments. We don't, as of now, have our own lunar lander or, lunar exploration program for that matter. So we have an overall exploration program in ESA called the Terra Novae, which includes LEO, Beyond LEO, Moon, and Mars. These are the 4 cornerstones. With respect to what else is going on, so the ISRU, the Indian Space Agency, just launched a mission. So they are also keen on getting to the moon. The Russians will launch a mission in August called Lunar 25. So they have their own lunar exploration program. And there's China, of course, which has been very successful over the recent years with lunar landings and lunar missions. They have recently successfully performed a sample return. They will perform the next sample return with Chang'e 6 mission. And they are astonishingly successful with their missions. So this is a very strong program. That's the major players in lunar exploration right now. So as you see, a lot is happening. There's a lot of international collaboration going on, which is something completely different as compared to the former race to the moon in the 60s, 70s. So yeah, the whole perspective has changed a bit, but there's a lot going on.
You already mentioned the new participants of the new space race, like India or China. What can we expect from them in the future?
So, from China, they have a very long-term roadmap. So they plan in decades, right? Not as for us, we plan in terms of 3 years, 4 years legislation periods. It's a very politically driven endeavor. For China, I think we can count on them fulfilling their goals in the next years. So they are planning. So I think they are now in the what they call the 3rd phase of their program, with establishing, ultimately to establish a base there on the moon. And currently, the main objective is to return samples, to also land in the South Pole area, because no one has ever landed there. And so I think we can expect a lot happening from them. The Indian mission that has just been launched is they have an orbiter and a lander. The last lander of the Chandrayaan-2 mission unfortunately crashed. So of course they want to repeat this attempt to land softly on the moon and use the rover to explore the lunar surface. They're also targeting the south pole area, which is a first. Actually, no one's ever landed there or put a rover there. This is what to expect immediately. And so from the other players, apart from the US / European collaborations.
What are some challenges of landing the rover at the south side or the far side of the moon?
Well, as it stands, landing is the biggest challenge for lunar missions because we saw lots of failure in the past. The very recent one of the iSpace mission, we had the Israeli mission a couple of years ago, 2019, I believe it was, with the Bereshit lander, and we had the Chandrayaan-2 failure. So apparently this is still a big technical challenge or operational challenge. And for the south polar area on the moon in particular, the terrain is challenging. Also the terrain in combination with the lighting conditions, because it's rougher terrain. We have lots of craters there. The craters are interesting to explore. This is why we want to go there. And there are a few challenges that are just there in general, but there are a few special ones depending on where you want to go.
Yeah. In the last space race, only governmental institutions were involved. And this time, or nowadays, we have also private companies like SpaceX or Blue Origin that are contributing to this missions. How do you assess their influence?
So the influence of the private companies is critical. The US will not be able to land a person on the moon without the contribution of, for instance, SpaceX. So they're counting on SpaceX to land humans on the moon. So the companies are now in the critical path of the mission, of the overall architecture of the US. So their influence is naturally quite high.
You said NASA or USA needs SpaceX as like for the rockets, but they have the Artemis missions. Why can't they use them only? Or what is the benefits of the private companies?
So in general, the idea is that you can make things quicker and cheaper and spread the risk, basically. In comparison to developing one single big launcher or one big lander, you have multiple providers of that, so the risk is reduced. And if you adjust as an agency to the to how the companies work, you can also potentially speed up things in terms of realizing the missions.
Yeah. And this or that questions, you picked Artemis. What improvements of technology do we have at Artemis that we didn't have at Apollo?
In terms of technological advancements, I think there's a lot. I would more draw it to the political differences or the differences in how we approach the missions, because this is the main thing that changed, right? So whereas Apollo was only about from the US perspective to beat the Soviets in reaching the moon, this is not the goal anymore. So the objective is now to explore, to perform science, to also collaborate internationally. This is the main difference as compared, or the main advancement that has taken place over these 50 or 60 years. So in terms of technology, I mean the architecture is very much different. So now we have an element such as the gateway that would allow us to perform science in lunar orbit, but also to access the surface or perform lab analysis on the gateway as compared to returning samples back to Earth before analyzing them. So this is a new element, the capability of landing really large masses on the moon with an HLS, so the spaceship of SpaceX, or the Blue Moon, or the Argonaut, is also new. So we want to establish an infrastructure there on the moon and around the moon. And this requires new technology, new launcher capability, new flexibility. And so that is new, first and foremost. So there's smaller technological advancements as compared to the last space race. And of course, they are on all levels, basically. So there has been... systems operating on the lunar surface now have to be or can be autonomous, for instance, can be teleoperated. So you don't require humans everywhere in the loop. Of course, you still require them, but there's a lot more that can be done autonomously. The whole landing will be done autonomously. We have hazard detection and avoidance, for instance. So no one has to fly a landing vehicle manually any longer. These are just a few examples of what has been taking place in terms of advancements.
Yeah. Now we're getting straight into your research field and focus on ISRU. We should clarify first for everyone what ISRU incorporates. So what is ISRU and how would you define it?
Okay, so ISRU stands for In-Situ Resource Utilization. That means that you don't bring all the resources with you on a space mission, but you find them where you are, so in situ. You mine them, you extract them, and you utilize them. So this is in-situ resource utilization. I should say there's also another term called SRU, space resource utilization. That is more of a broader term that also means that you could potentially mine asteroids and bring them back to Earth to use metals, for instance, or so precious metals. But for ISRU, in-situ resource utilization, the main scope is to use the resources right where you find it, meaning in space.
So there are different steps of ISRU. The first one would be starting with the mining, the prospecting. And you brought some device today. Could you explain what this is?
Yeah. So naturally, the first step in what we call the ISRU value chain, because ultimately we derive a product that we cannot use or sell. The first step is prospecting. So prospecting means basically detecting resources. After prospecting comes the exploration. Exploration means assessing the value of the resource. But prospecting is the first step. So what I have here is an instrumented drill. It's hollow in the inside. There's a central heating element inside. And there's a mass spectrometer that you don't see because it's not connected, but which would be connected to that drill.
Yeah, I can imagine, yes.
So what we try to do with this instrument, once it's on the lunar surface, is we put it on a rover, for instance, and then we drill down to 10, 15 centimeters depth, and we heat the material that is enclosed by the drill. And by heating, volatile species will be extracted. So everything that is temperature sensitive, like, for instance, water. And with a mass spectrometer, we will be able to characterize what is in the shallow subsurface. And so the idea is we use the rover to drive through an area and take multiple samples and therefore map potentially the resources that are there. And with that map, we can then further go into the next phase of exploration.
Okay, so now we're not on Moon, we're on the Earth, and we have this drill right here. I guess there needs to be some method to kind of simulate the lunar regolith to test out these devices, those drills in your lab right here.
Right. So we have, of course, real lunar regolith. So regolith is the term for the lunar rocky material, the soil. We have real regolith brought back by the Apollo astronauts, but also the Soviet missions, but also the Chinese mission. But this is very expensive, and you cannot just only go to the curation facility and take it. So you have to apply for that. You have to write a proposal. What you are going to do with that. You have to make sure, in some cases, not to destroy the material or to alter it. So for our purposes, this is not a solution, but it's also not necessary because we can simulate regolith with so-called simulants or analog material. And that is just also rocky material that has the same or a similar enough composition. Also in terms of particle size distribution, angularity of the particles, physical properties. There's a variety of simulants available nowadays from different sources, and this can be used, for instance, to perform the drill tests.
Okay, and now, before prospecting some resources, how do scientists identify potential resource-rich areas on the moon? Because first you need to find some landing site for the lunar lander and say, yeah, that is a good location to find interesting resources.
Yeah, so this is also part of the prospecting campaign now, if you will. This is done mainly through remote sensing. So through spacecraft in lunar orbit that, for instance, take reflectance spectroscopy and thereby identify minerals at the surface. There's also other techniques that penetrate through the surface layers and can sense, for instance, materials in the shallow subsurface like radar. So there's a whole different set of techniques that is also employed for planetary science in general, but also Earth observation that we can use on the moon. And by that we find sites of interest. In terms of prospecting for lunar water, it's a bit difficult because we have only a few measurements from orbit. Some of them are also contradictory, but there's a trend. So we think we know where to drill for water.
Why is the water on Moon so interesting? Because, I mean, there's plenty of water on Earth. Why is it so interesting and important to really characterize this water on Moon and to analyze it?
Yeah, so there's two sides to that. So one is the scientific interest, because we want to know where the water is, where it came from, so the origin, the form, the abundance, how it varies. So these are all questions that we don't have an answer to. So this is the first, the scientific interest to characterize water on the moon. The other interest is, of course, economically, because ultimately water is a resource that is used by humans on the moon in the lunar base, that is also used to make propellant, to drive rockets, and it's much cheaper to get that water from the moon as compared to the Earth.
There are those ideas to get water on a large scale and then transfer it to rocket propellants to have some hub to store it to other planets, especially exactly. Plans to go to Mars from there.
Yeah.
How feasible would this be?
Oh, it's, technologically it's very feasible. Of course, there are a few challenges along the way, but I think it's not too difficult. So, I mean, the whole idea, as you correctly mentioned, is to build up fuel depots on the moon or in lunar orbit, because bringing it there from the moon is much more cheaper than bringing it there from the Earth, right? And technologically, you would just have to find water to access it. So you need some sort of drill, mining device, depending on how the water exists. If it's at the surface in terms of like a frost layer, you would need something like a dome structure to heat it, extract it, and collect it. If it's in the subsurface, of course, you need to drill, excavate it somehow. In any case, you will always have to separate the water from the regolith or from contaminants. So this is one of the bigger challenges, perhaps. And then also the storage of the products, if it's water or if it's hydrogen and oxygen, can be a challenge because of temperature issues or meteoroid impacts or other hazards that exist on the lunar surface.
Yeah, definitely. I would like to focus a bit more on this second aspect in this ISRU chain, the characterizing. Could you give some more details about what is involved in this characterizing step and which instruments are used to characterize maybe water or other resources?
So when we talk about characterizing water, what we mainly mean is to find out the isotope ratios, because by that we can tell something about the origin of the water, where it came from in terms of where in the solar system. And so this is done by mass spectrometry, as we have it here for the drill, but other systems that are more precise in terms of measuring isotopic ratios. And for that, you need to thermally extract the water molecules. And for that, you use heated drills like that, or small crucibles where you put the samples in and heat them up. And you do something that is called the evolved gas analysis to analyze gases that come off. And then you can also, with a more sophisticated instrument, characterize them, as I said.
I see, but still it seems kind of highly technically involved to bring those instruments there and then make sure that you characterize it correctly.
Yeah, that's true. So here on Earth, we use all this analytical capability on a daily basis. So this is not a challenge per se, but the challenge is to really, as you correctly said it, to miniaturize it, to make it space ready, to make it radiation hard in terms of electronics. That is a challenge, and to make it work on a low resource budget.
Yeah,
meaning low. You have less power available. You have less mass and volume in total. So the usual challenges of a space instrument. But there are actually good examples of, for instance, mass spectrometers that have been working in space, also in other environments similar as the moon, similarly extreme as the moon.
Okay. Apart from the water, because now we talked much about characterizing water on the moon, but which other resources would be of interest?
So the regolith, the soil itself, is a pretty good resource because one, you can extract oxygen from it, and two, you can use the regolith to build structures. So you can build roads, landing pads, shelters, habitats. So you can make a lot out of the soil itself. Then, as I said, you can extract oxygen, you can extract metals too, you can also extract noble gases that were implanted by the solar wind. Is admittedly one of the smaller resources, but so the regolith itself holds many potential products that we can use in exploration. And of course, the sun itself is a resource on the moon because I can collect it nearly everywhere. There are challenges associated with that, for instance, the dust contamination, but this is a very important resource in terms of power provision.
I also came across this isotope helium-3, reading articles and saying this might be the reason why so many nations want to go to the moon. What's your opinion on that?
Well, naturally, if we can manage to make helium-3 fusion or fusion in general work, this is a very tempting thought, right? The abundance of helium-3 is not that high on the moon, actually. So we can also get it here on Earth. Problem is that the accessibility here on Earth is a problem because it's locked in the Earth's crust. So we cannot just mine it properly. If we had a fusion reactor, then it might be worth mining it on the moon. But we're speaking of several parts per billion in terms of quantity in the regolith. So you have to mine huge amounts of regolith and to extract tiny little amounts of helium-3. and you also need to do something with everything else that you extract along the way. You would not only go for the helium-3 in that case, you would also try to collect other things that you will extract thermally on the way to getting the helium-3 to make it more economically viable. Yeah. So helium-3 is not the driving argument for lunar exploration or for ISRU on the moon at all.
Yes. Okay. This definitely makes sense. But you said there could be also other resources obtained at the same time. Would there be any commercial interest, or as of now, is it just scientific interest in extracting and characterizing those resources?
So the one resource that is really interesting from a commercial perspective is the water, because it is more or less readily available and is needed by humans and rockets, if you will. So it's just a very useful resource because you can utilize it in so many ways. And we're also so it's not entirely new technologies that we need in order to do that. Apart from that, I mean, from the commercial perspective, I think really it's the water that is most interesting. Because also other resources like extracting the oxygen from regolith require a different infrastructure, also might require more power, might require resupply missions, so they're not fully independent. But we're currently thinking of different ways to establish a business case for the mining of water. And one idea here is that commercial entities would go to the moon, mine water, provide it in terms of, gas stations, if you will, on the moon or around the moon, and then agencies would buy the water from them. Agencies would be the anchor customer for this business case to kickstart an economy that evolves around that. And there is this can be a really serious business, and we're currently working on that. Of course, there are questions still to be answered. The whole exploration of lunar water needs to take place in situ. We need to really know for sure what the abundances are, where the locations are, and so on and so forth, to really convince a commercial partner to go there and set up a mining endeavor.
When thinking about this mining process, extracting resources from a celestial body in outer space, there's also some moral aspect to it. The legal framework surrounding this ISRU remain kind of ambiguous because there's this foundational Outer Space Treaty of 1967, which is instrumental in guiding space law, but it does not explicitly address this lunar mining. And additionally, there's the Moon Treaty of 1979, aimed at preventing international conflicts that could happen on a place like Moon, where there's this interest for mining, maybe a commercial interest, but it wasn't ratified by any space powers, by any states that are influential in crewed spaceflight.
Yeah.
What do you think? Where does scientific research end and commercial interests come into play, and how should this be regulated?
That's a very hot topic right now. And we'll speak about planetary protection, essentially. So whereas on Mars, we need to make sure that we don't bring in any species, the story is different for Moon, but it's also part of the planetary protection. And there are examples on how to deal with that. One example is to say, look, you can mine something at the South Pole, but leave the North Pole. Yeah, don't touch it. Because it's a similar environment, also similarly interesting from a scientific perspective, but currently not really addressed by any of the overall architectures. So the idea would be to set up restricted zones, areas on the moon where no mining is allowed to take place in order to preserve that natural environment. Of course, it's not so easy because once you disturb an area, say at the South Pole, through, because you don't have an atmosphere on the moon, through interaction with the regolith there, also contaminants and dust will circulate the whole moon. So everything you do on the moon on a larger scale in terms of mining operations will ultimately affect the moon globally, right? This is just how the moon works. The moon is a rather small body, don't has an atmosphere. So you add a lot of contaminants, for instance, just only by landing a SpaceX Starship. I believe I read somewhere that the exosphere of the moon, so all the elements that are in this tenuous atmosphere, sum up to about 50 tons. And so you would easily add quantities in the same order of magnitude by just adding the exhaust gases from rockets. And then with a mining operation, you stir up a lot of dust. This will get distributed globally. Water will get lost, will migrate somewhere else. So once you really start a large-scale operation of ISRU on the moon, there's no way to really protect these restricted areas. Although, of course, you can still and you should still do that in order to allow investigation of for instance, subsurface layers that are more protected by these interaction with what is happening elsewhere on the moon.
So you're saying sustainability is not just a thing on Earth, but one also needs to think about the effects those explorations could have on the moon in this case.
Yeah, definitely. So sustainability in space exploration has many aspects, but we should really try to regulate or try to find a regulation that fits all the purposes, which, as you can imagine, is quite challenging.
Do you think there's a threat to have some monopolistic environment on the moon? Because, as we said, there are not too many companies having the capabilities to just access places like moon, and therefore it could be very likely that in some years there will be some monopole there.
Yeah, I mean that's quite likely, I would say. There is the attempt to distribute the responsibilities and the obligations of nations being active on the moon, perhaps through the Artemis Accords. Also saying that the operations on the moon should not interfere with each other. But the question then is, how is this controlled and how is this protected? And so yeah, there's a lot of unknowns. It'll probably just be a Wild West scenario. But yeah, we shall see.
Yeah,
it's hard to predict that.
Yeah, it's really hard to predict. We need to see. We need to wait for the future to come.
Now we're going to focus on the main goals of lunar and planetary exploration. What are the main goals?
That's a big question. Well, I would say the main goal is to expand our knowledge. Right. So this is the focus of all the missions that are there now in space, interplanetary missions, solar system exploration. The main purpose is science, to perform science, and the purpose of science is to expand our knowledge, to understand how things work, to understand how the solar system works, how the universe works. So this is the prime purpose. Of course, there's other sides to it as well. So there's just this natural curiosity of humans to look around the corner and see what's out there, right? So the inspirational aspect that keeps us exploring, not only in space, but also on Earth. And to ultimately perhaps expand humanity beyond the limits of Earth. Yeah. So this can be a motivation too.
You already talked about expanding our knowledge. How does lunar and planetary exploration contribute to our understanding of Earth and its history? In what ways does it impact our everyday lives?
So we go to the moon to explore not only the history of the moon, but by that we also explore the history of the Earth, because they have a common history. They're in the same system. The moon orbits the Earth, and other than the Earth, where you have humans living on Earth, weathering processes, there's a lot of activity on the Earth, whereas on the Moon, everything is recorded and preserved, like in a natural in a natural museum. So the history of the solar system is recorded there, meaning, for instance, how the solar wind composition changed, how the bombardment history was, and by that we learn about, for instance, how water has been delivered to the inner solar system, how potentially life evolved on Earth. So that all is interconnected in the solar system, because it's not a static system. It's very dynamic. It has been very dynamic in the past, and so everything we can learn from this natural museum that we call Moon also traces back to what our Earth has experienced.
Often also is asked, is it really necessary to fly to the Moon or Mars when our planet is suffering from climate change?
Yeah, I mean, why not? So the space exploration is also driving technological advancements. It changes the way we look at our own Earth. It provides us the advancements that we need in order to observe our Earth and learn from our Earth. So the whole observational aspects. And it's not expensive. So in contrast to what people often think, space exploration is not very expensive. So I read a figure once that said the average amount that a European taxpayer in one of the ESA member states pays for ESA's entire space activities is 10 euros per year. So about the same amount you pay for a cinema ticket. And while with inflation and everything, this has grown a bit, you can see the figure is not that large. And from this, you get all that ESA does, from Earth observation, detecting, wildfires, floods, everything that we need in order to understand what's going on here on our planet, but also the whole exploration. So going to Jupiter, for instance, so that all is interconnected. And we need space exploration. I'm convinced we need space exploration in order also to expand our knowledge, but also to satisfy our natural curiosity and find out what happened, for instance, on other planets, like Mars, how the climate changed there, and how this affected everything that was going on that planetary surface. So if we were just looking around here on Earth, not being able to look from space, to look into what's going on elsewhere in the solar system, the knowledge that we would have right now would be much less, and we wouldn't be able to understand really how to fight climate change.
Yeah, there's so much knowledge we can obtain from space exploration that will help us on Earth. And also, when thinking back of the podcast we did with Professor Walter, he also said that it has a big impact on your mindset, just leaving this system Earth to enlarge your horizon, and then think about possibilities, solutions for having positive impacts.
Absolutely, yeah. We tend to think in boundaries here on Earth, whereas once we are out there, these boundaries disappear, right? And that also helps a lot in driving political decisions or motivating to change one's mind.
Yeah. So potentially in the next decades, could I look up to the sky at night, to the moon, with some professional telescope, and then see a moon base where people live on the surface of the moon?
Potentially, yes, but I mean, the moon base really is still many years in the future.
Which time frame are you thinking of?
That's a very good question, and so maybe we will see something in the next decade. in terms of a rudimentary base. It might be by the Americans, might be by the Chinese. The long-term visions or strategies, they don't really go that far as it stands right now. But we're working towards that. And so giving a time for that, a date, is really difficult.
But for humanity, just in general, we might be right now on the verge of calling Moon our second home, because it could happen in the next decades.
Yeah, so we will for sure see not a permanent, but an intermittently occupied gateway around the Moon, and later on we will see stations where from time to time people will work and live. Maybe not permanently at first, but then, with time.
Would this be restricted to science, or I would assume there must be some point where there is also this idea of having some sort of tourism, especially when prices for bringing mass up to those places will be cheaper.
Yeah, I guess we can expect that space tourism will always play a role. Definitely. But science will be the main driver, at least I hope. Then commercial activities, we shall see how they evolve. But this will be necessary. I don't think we can build up a station on the Moon without this commercial aspect, or with the ecosystem of mining and selling space resources, because otherwise it will just not work. A moon base will not be possible if we rely on bringing everything from Earth. And this is for sure.
Yeah,
so we will see science,
that's where the resource utilization comes into play.
Exactly. So resource utilization, and that will probably not be driven by agencies, but by commercial partners. So we have both sides. We will have both.
Yeah. Technically, then it would be absolutely possible to achieve some environment on the Moon where humans could live. But what would be physiological and psychological challenges still to be faced?
I mean, there's a few challenges along the way. Not only the resource aspect, but also things like navigating, communicating. This is why we want to set up a global navigation network around the Moon, for instance. In terms of psychological challenges, of course, we have the extremely long lunar day and night cycle, but it depends on where the station really is, and how it will be operated. So perhaps people will change back and forth from the gateway and the station, and not be there during nighttime. It also depends on the way we provide power to a lunar base. If it's solar, then we're restricted. Psychological aspects are a thing, and are a problem. But I think not so much actually for lunar operations, because the Moon is very near. You can always get back. You're not that remote. So in case of an emergency, you can travel back to Earth rather quickly. You can always go back. You don't need a certain window as for Mars transits, for instance. And you always see the Earth. And that also feeds into psychological problems a lot. So really, I think that is less of an issue for Moon, much less as compared, for instance, to Mars exploration.
Yes, and going to Mars would take so much more time. There are only specific time windows where you can go there and where you can go back to Earth. That would definitely be much more challenging than for Moon.
Yeah, the journey is longer, and just a mere aspect of the Earth getting smaller and smaller, and at some point you maybe don't even see it properly. That is a big factor, I believe.
Yeah.
Now we want to talk about your future in academia. Which direction are you targeting for your future research?
Yeah, the long-term perspective is certainly to build instruments that fly to the Moon and beyond. We are currently working on that. We have different contributions in actual missions, and we all want to explore other places too. This is why my group is called Lunar and Planetary Exploration. So planets or planetary bodies are also part of the game. And so this is the long-term goal, or the maybe not so long-term goal actually, to be able to provide instrumentation for Europe's space exploration programs and contributions to other missions, and really bring hardware to places where no one has ever set foot before, or assist with lunar exploration, and provide the methods to produce breathable air on the moon.
For these successes, you need collaborations. Are there any collaborations with other chairs?
Yes, of course. So the space group here at TU Munich is still growing. We are currently 4 professors working on topics like satellite development, propulsion, life support systems. So naturally, there are some links. For instance, ISRU also means providing propellants for rockets. So we're currently working on a concept that shows extraction of ice from regolith, all the way down to that ice being used to propel a rocket. So an end-to-end demonstration of that concept. And this is in collaboration with Professor Manfletti's chair. There's other natural interfaces to Professor Detrell's chair, who is working on life support systems, which are also sort of at the end of the ISRU chain, the utilization part. So we are collaborating closely there too. And for the small satellite developments, we're also collaborating a lot, because we build instruments that we want to fly on small satellites. For instance, one development that we're currently pursuing is a dust detector that can ultimately also be used to characterize dust in the lunar environment. And as small satellites are becoming more and more important for exploration. For instance, we had small satellites on the DART mission recently that impacted an asteroid. We had small satellites accompanying Mars missions. So this is also a growing field in space exploration. So there are very many links to the other chairs, and we're very closely collaborating here at the Ottobrunn site.
Now also speaking about future missions, are there any upcoming lunar or planetary missions that you find particularly exciting or promising?
Lunar, yeah. Well, basically, all of them are exciting, right? So I'm more excited by those who actually land on the surface and operate on the surface, I'm really keen on seeing the next landers landing successful there, because this means we are actually entering that new era of having commercial transportation services to the moon, which for us as scientists, researchers, is the opportunity to bring our instruments there and perform our research, not only here in the labs in an analog environment, but there on the moon. So this is very important for us. Of course, human landings on the moon will also be fascinating in itself. So I'm very much looking forward to the Artemis 3 mission, where for the first time after the Apollo era, people will set foot on the moon again. Potentially then in the next years also with a European astronaut. So this will be particularly interesting for us. So these are the ones I'm looking forward to. But I really cross fingers for all of the future missions to be a success, because we rely on the success of every mission to really sustain that current that current race to the moon, if you will.
For the crewed mission, that's definitely history being made again. But right in the beginning, I asked you in the this or that, crewed mission or rover mission, and you said rover mission. Could you also explain why this is so interesting for you?
Yeah, I mean that's a long-standing dispute between people advocating for robotic exploration, others for human exploration, space exploration, and you definitely need both. So it's not a question one or the other. It's always one with the other. And but I myself do focus more on robotic missions because I also want to go to other places farther out in the solar system, and this is just very difficult with humans currently. So this is why I favor the robotic.
Yeah, I definitely see the point there. How do you see the role of robotics shaping the future of lunar and planetary exploration? Would you say this is just a first step?
So the role of robotics is to so in lunar exploration will be to assist humans and complement the activity of humans, because for some tasks you need humans, for some tasks in very extreme environments, for instance, you need robots. So they complement each other. In the long term, this will probably stay that way. I don't see that one or the other will get more dominance over the other. So it's about the human robotic interaction and the how they can work together.
Before we now come to an end, I have one last question. What advice would you give to aspiring researchers or students interested in pursuing a career in lunar and planetary exploration?
Do it is the immediate response. So the times are pretty good right now to step into a career in the exploration world. Naturally, I mean, exploration also starts here on Earth. So explore your study program, explore places to go, universities to study, to spend like a summer semester, explore companies, do your internship there. Take your time during the study, because that is what pays off in the end. Do projects. We have a cool student group here where you can engage in cool projects. There's other projects provided by ESA and DLR. Gain hands-on experience, just look around you and find out what's for you and train yourself. So it doesn't matter if your study then takes like 6 months longer than the regular study program. If you have gained a lot of experience doing cool things, and there's a lot of opportunities, especially here at TU Munich with the student group and with the courses we offer and with the connections that we have to industry or to the agencies. So approach us, the professors, the research assistants, if you're interested, and just explore the space around you.
Thank you very much for joining us today, Professor Reiss, and for the great insights in your field of research.
Thank you.
Be sure to stay tuned for future episodes and don't forget to subscribe or like this episode. Thank you for listening.